An electric cooking range is a combined structure of a hot plate and an oven. It contains a highly efficient heating element and better cooking controls for every possible kitchen need. The surface heating units are set in the top of the range and the oven is placed beneath it. The selector switch is rotary in type, which can select 4 to 6 different levels of heat. The step switch is connected to 2 or 3 elements of 230 volts. The total circuit resistance is changed to provide different levels of heat. Increase of heat is achieved by connecting more elements in parallel. For low heat, the coils are connected in series. The oven unit consists of 2 heating elements, an upper and a lower element. The temperature of the oven is controlled by the thermostat and a timing device, while the broil unit is constructed by stringing the element through the frame in 2 separate coils. The baking unit is strung with a single coil. Always study the connection diagram given by the manufacturer or trace the connection of the cooking range. Check the continuity of the surface unit element one by one. Replace it if found defective with the correct shape, wattage, and voltage. Measure the insulation value between the terminal to body of the appliance at various positions of all the switches. The value should be more than 1 megohm. Let's see some of the common problems that may arise in a cooking range. If the oven does not heat, it might be due to the selector switch being off, the fuse being blown, an inoperative oven control, oven element circuit is open, or the timer is inoperative. If the oven does not turn off, this might be due to faulty thermostat calibration, improper oven door fit. If water drips in an oven or it sweats, it might be due to oven not preheated with door open, excessive oven temperature, door is not sealed properly, a clogged oven vent. If the surface unit does not heat, it can be due to blown main fuse, inoperative switch, unit circuit is open. In this section, we have covered the various parts of a cooking range, apart from attending to certain minor problems in the cooking range. A megometer, commonly known as an insulation tester, is used for checking insulation resistance and continuity. In this section, we're going to see various types of insulation testers, parts of the insulation tester, ranges of the magneto-generator type insulation tester, constructional features of a transistorized insulation tester, safety precautions to be observed while using an insulation tester, and the uses of an insulation tester. Ordinary ohm meters are not generally designed to measure high value of resistance. An instrument exclusively designed for this purpose is the megometer, commonly known as a mega. There are 2 types of insulation testers, the magneto-generator type and the transistorized type. First, let's see the magneto-generator type tester. In this, the testing voltage is produced by a magneto-generator when the handle is cranked at a speed of approximately 160 RPM, whereas the transistorized type has cells incorporated in it which power the tester. The megometer consists of a small DC generator, a meter calibrated to measure high resistance, and a cranking system. The speed at which the armature rotates does not affect the accuracy of the meter. However, it is recommended to rotate the handle at the slip speed to obtain a steady voltage. As megas are designed to measure very high values of resistance, they are used for insulation tests. A 50,000 megohms 2500 volts mega is to be used to test high tension equipment, transformers, main supply, etc. For testing power circuits, motors operating on voltages not exceeding 500 volts, a 2000 megohms 1000 volts mega is to be used. For testing house wiring and small motors operating on voltages not exceeding 250 volts, megas of 50 megohms 500 volts can be used. A transistorized mega is an electronic insulation tester. It converts low DC voltage from a dry cell to high DC voltage by using an oscillator, step-up transformer, and a converter. The voltage generated at the test terminals is in the order of 250, 500, or 1000 volts depending upon the design. A moving coil meter with a high resistance in series forms a series ohm meter and has a dial graduated in megohms similar to the conventional mega. Zero adjustment can be made to compensate for the voltage variation as the cell discharges. This can be done by shorting the terminals and setting 0 before any measurement. Multi-range insulation testers are also available. This is provided with the selector switch to change the range. Now, the precautions while using a mega. A megohm meter should never be used on a live circuit. The handle of the megohm meter should only be rotated in the clockwise direction. Do not touch the terminals of a mega while conducting the test. Always rotate the handle at slip speed. Now let's see how to test the continuity of a cable using a mega. First, test the mega for its proper function. Keeping the two terminals open, rotate the handle at about 160 RPM and observe that the pointer reads infinity. Next, short the two terminals and rotate the handle and confirm that the pointer reads 0. To test the continuity of the cable, connect the two terminals like this. Rotate the handle at the rated speed steadily and record the reading of the mega. In this section, we saw the functioning of a mega, the different ranges, and the procedure for measurement of insulation resistance. Light is a form of electromagnetic radiation. Visible light rays travel in the form of waves, having a wavelength, and the difference in wavelength produces the effect of color in light. The various types of electric lamps available in the market vary in construction and in principle of operation. They are broadly divided into three: filament lamps, arc lamps, and the discharge lamps. Filament lamps give light as a result of heating the filament to a very high temperature. It's a lamp in which a metal or carbon is used in a wire form to produce white light by the passage of electric current. They are called incandescents. Filament lamps are further classified as carbon and tungsten lamps. The carbon filament lamps made today have limited application. This lamp gives a reddish light and operates at a temperature of about 2000 degrees centigrade. Above this limit, the carbon evaporates rapidly and blackens the glass bulb. The output from a carbon filament is about 3 lumens per watt. The tungsten filament lamps consist of a fine wire of tungsten metal as filament in a vacuum bulb. Filaments are now made of tungsten due to its exceptionally high melting point. It operates at a temperature of 2300 degrees centigrade and has an output of about 8 lumens per watt. Filling the bulb with an inert gas like argon and nitrogen reduces the rate of evaporation, increasing the operating temperature to about 2700 degrees centigrade. The light output is about 12 lumens per watt. A tungsten filament lamp in which the filament operates in a relatively small space with an inert gas and a halogen is called a halogen lamp. The GLS or General Lighting Service filament lamps used at home have a bayonet cap. Some lamps have an Edison screw cap. Edison screws are favored for spotlight, in which lamps must be accurately positioned. Each of them can be fitted in their appropriate holders only. The rated life of a General Lighting Service lamp is about 1000 hours. A lamp in which the light is obtained by discharge of electricity between 2 electrodes in a gas or vapor medium is a discharge lamp. Fluorescent lamps come under the category of discharge lamps. Talking about a fluorescent light bulb, it is basically a glass tube capped by 2 bases. These bases are fitted with pins to carry current to internal components called cathodes. The inside of the tube contains minute droplets of mercury and an inert gas. The inner surface of the tube is coated with a fluorescent powder. This emits visible light when exposed to UV rays. The starter, choke, and the tube's electrodes are connected in circuit as shown here. A choke is basically a single winding small transformer unit. It has 2 functions. Initially, it steps up the supply voltage to start the electron flow through a gas medium in the fluorescent tube. Then, while the tube is conducting, it regulates the flow of current to the tube cathodes to prevent them from burning out. A starter in a fluorescent tube has 2 functions. It completes the circuit first for preheating the electrodes. It opens the circuit to provide voltage kick for ignition. The light output of a fluorescent lamp amounts to about 70 lumens per watt, and it's available in various wattage. The normal lifespan is 3000 hours. They are affected by both high and low voltage. The more often a fluorescent lamp is turned on and off, the shorter will be its lifespan. To check whether a choke is open, connect it to the test lamp in series. If the lamp glows, it means the choke is okay. If the test lamp does not glow, then a choke is open. If found defective, replace the choke with another one of the same capacity. To check whether the starter is open, connect it to the test lamp in series. If the lamp flickers or blinks, it means the starter is okay. If the test lamp does not glow, then the starter is open. After checking the accessories individually for their proper working, connect them as shown in the circuit diagram. This is how you assemble a fluorescent lamp unit. After fixing the accessories in the fitting base, give firm connection to the terminals by using a flexible PVC wire as shown in the circuit diagram. Next, insert the tube lights, turn them by a quarter turn in their position and switch on the power. By adjusting the tube lights a bit, you could see the lights glowing. Okay, now let's see some of the common problems we face in a fluorescent light. If the light fails to start, it could be due to a filament burnout, broken tube lamp pins, defective starter, broken lamp holder, an incorrect tube or choke. If the tube glows at the ends but not at the center, it might be due to faulty wiring, fixture not adequately grounded. If the ends of the tube are black, it means that the tube's active life is over. If the tube flickers or blinks, it might be due to tube pins making poor contact, tube nearly burnt out, defective starter. In this section, we have learnt about the various types of light bulbs and their principles of operation. In this section, we're going to learn about the way of assembling a decorative serial lamp set for 240 volts AC using 6-volt bulbs as well as the flashers. The lamp filament operates at a very high temperature of 1800 degrees centigrade to 2200 degrees centigrade. The resistance is nearly 12 times more when the lamp is on than when it is off. Now, let's see how to calculate the resistance. If the voltage is equal to 240 and the wattage is equal to 60, then current is equal to wattage by voltage, which is 60 by 240, which is 0.25 amps. Then the resistance is equal to voltage by current, which is 240 by 0.25, which is equal to 960 ohms. Similarly, if the voltage is equal to 24 and wattage is equal to 40, then the current is equal to wattage by voltage, which is 40 by 24, which is equal to 1.667 amps. Resistance is equal to voltage by current, which is equal to 24 by 1.667, which is equal to 14.4 ohms. When we have to connect a row of 6 or 9 volt lamps, if the lamps are connected directly to 240 volt supply, the lamps will get fused immediately on lighting. Therefore, the lamps have to be connected in series. If the voltage of the lamps are 6 volts, then the number of lamps that will be required are 240 by 6, which is equal to 40 lamps. And this is how the lamps are connected in series. We get bulbs of the same voltage but different current ratings in the market. It may be 100 milliamps, 150 milliamps, 300 milliamps, or 500 milliamps. To assemble a serial lamp set after determining the number of bulbs required based on the voltage of the bulbs, connect the holders in series with suitable lead lengths. Test all the bulbs and fix them in the holders. Connect the lamp set to the main supply and test them for their glow across the 240 volt supply. Switch off and now add a flasher bulb in series and check its working. With the flasher bulb connected in series, now the series lamp set should flicker. Please note that for the series lamps to work satisfactorily, the current rating of all the lamps should remain the same. But we can have serial lamps of different voltages but of the same current rating connecting together. Let's assume that we have 25 lamps of 6 volts and 20 lamps of 9 volts, all of 300 milliamps rating. Now, to design a serial lamp circuit for 240 volt supply, this is how we proceed. If we want to use all the available 6 volts bulbs, the voltage drop for 25 lamps of 6 volts in series will be 25 into 6, which is equal to 150 volts. Deducting this from the 240 volt supply, the voltage remaining to be dropped is 240 minus 150, which is equal to 90 volts. The number of 9 volt lamps in series is equal to 90 by 9, which is 10 lamps. So, 25 numbers of 6 volt lamps and 10 numbers of 9 volt lamps can be connected in series across the 240 volts mains. Alternately, if we want to utilize all the 9V lamps, then the voltage drop across 20 numbers of 9 volts lamps is 20 into 9, which is equal to 180 volts. Voltage to be dropped by 6 volts lamps in series is equal to 240 minus 180, which is equal to 60 volts. So, the number of 6 volt lamps in series is 60 divided by 6, which is equal to 10 numbers of 6 volt lamps. So, 20 numbers of 9 volts and 10 numbers of 6 volts can be connected in series across 240 volt mains. It is always safe to keep the number of bulbs in series more than the calculated numbers. This is to reduce the current through each lamp slightly. The reduced current decreases the chance of fusing of the lamp when the voltage of mains is increased by chance. Now, let's see the use of the flasher and how it is connected in circuit. The flasher lamp contains a bimetal strip which is in contact with a fixed strip. When the serial lamps are switched on, the bimetal strip gets heated up and breaks the contact, disconnecting the supply to the chain of lamps. Again, when the strip cools down, it regains contact and the lamps light up again. 3 rows of lights connected with 3 flasher bulbs, as shown here, operating at the same time can produce a twinkling effect of the lamps. In case one flasher is to be connected common to the 3 rows, then the current carrying capacity of such a flasher in parallel circuit should be equal to the total current drawn by the parallel circuit as shown here. Though the flasher can be connected anywhere in the circuit, it is advisable to connect it near to the supply, considering it as a switch. This is the basic principle on which a serial lamp set is assembled. Why do we require a twin tube connection and what do we gain by it? In this section, we're going to learn about the advantages of using twin tubes, stroboscopic effect in lights, operation of twin tube connections in series and parallel. Unlike incandescent lamps, which emit constant light due to heat, fluorescent lamps extinguish itself every time the voltage wave passes through zero. It's approximately 100 times per second for a 50 Hz frequency power supply. If rapidly moving objects are viewed in this light, it could give a strange effect. This is called the stroboscopic effect. Though the flickering may not be noticeable under normal circumstances, danger can arise when moving machinery is present. Spokes of a wheel, when rotating at the same speed as that of the supply, appear to stand still. This could result in accidents when an operator touches the wheel thinking that it's stationary. To avoid this effect, modern tubes contain fluorescent powders which possess an afterglow to minimize the task period. This can further be eliminated by connecting adjacent lighting points to different phases of supply so that minimum of light occurs on different lamps at different times. Twin tube connections can be made in series as well as parallel. If the tubes are connected in series, then it is possible to connect them with two 20-watt lamps and one 40-watt choke. However, each lamp must have its own starter. This is also called a tandem connection. After checking the accessories individually for their proper working, connect them as shown in the circuit diagram. A 40-watt choke and two 20 watts 110-volt starters are to be used for the purpose. Next, insert both the 2 feet tube lights into their respective holders. Turn them by a quarter turn in their position and switch on the power. By adjusting the tube lights a bit, you could see both the lights glowing. The stroboscopic effect can be avoided by wiring twin lamp fixtures with one lamp wired inductively and the other with a leading current by the use of a capacitor. While the normal PF improvement capacitor is omitted, another capacitor of 3.8 MFD is connected in series with one of the lamps and the choke windings are dissimilar. The lagging current in one lamp is balanced by the leading current in the capacitor circuit. Thus, the currents and light outputs differ in phase by approximately 120 degrees and the total PF is nearly unity. To sum it up, the twin lights are connected in series by this way. They are connected in parallel like this with a PF improvement capacitor. A twin tube industrial fitting to counter the stroboscopic effect is connected like this. In this section, we have seen the advantages of the twin tube connection, the stroboscopic effect of light, and the series and parallel connections of twin tubes. We are now going to see some of the common insulation defects which eventually lead to faults. At the end of this section, we will be able to locate open circuit, earth fault, and short circuit in a domestic wiring installation. Some of the common problems that we might face are fuse protection not matching the current rating of the cables to be protected. This happens due to the equipment manufacturer fitting the fuse carrier with a fuse element of maximum rating than the fuse unit in the protection system. Incorrect use of material or material not corrosion resistant. Ends of the conduit not cleaned properly or bushing not provided. Use of PVC insulated cords instead of heat resistant type for connections in immersion heaters, etc. Use of braided and twisted flexible cords for bathroom pendant fittings. Use of cable of insufficient capacity to carry the starting current of motors causing voltage drops. In case of an open circuit, the appliance in the circuit will not operate. This fault can be located by use of a continuity tester. It could be due to a wire break, loose connection, blown fuse, or a faulty switch. And next is the earth fault. An earth fault between earthed metalwork and a live conductor will have the same effect as a direct short circuit. The circuit fuse will blow off. To locate the fault, first isolate the live conductor from the neutral by removing all lamps, etc. Keep all the switches in on position, and by using insulation resistance tester, the fault can be traced. The reading obtained in the instrument will be in low ohms range. It is important to rectify the fault, else it will cause a shock. And then the short circuit fault. Check the insulation resistance between the live and the neutral conductors with the tester. The reading will be in low ohms range. The fault can be precisely located by subdividing the faulty circuit and confirming the location of the fault. A short circuit can occur as a result of damaged insulation, bare wire in junction boxes, or loose terminals contact with a conductor of opposite polarity. A short circuit will lead to the fuse blowing off. Of all the faults, a high-value series resistance fault is the most difficult to trace. Due to this fault, the lights will be dim or the motor will run slow, thereby heating up. In a new wiring, wrong connection in the junction box resulting in 2 or more lamps being connected in series can lead to such a problem. In this module, we covered the various kinds of home appliances, their construction, their principle of operation, their general faults that could arise in them, ways of troubleshooting and servicing them. Thank you.
As you all know, electric motors are used to efficiently convert electrical energy into mechanical energy. Electric motors are found in household appliances such as fans, refrigerators, washing machines, air conditioners, vacuum cleaners, microwave ovens, water pumps, and so on. Apart from these, motors are vastly used in various industrial applications as well. Rewinding a motor is the last desperate step to take in repairing the motor. You can't usually tell if a motor needs rewinding by just looking at it. Motors need to be rewound generally for 2 reasons. Because excessive heat has damaged the insulation to such an extent that electricity passes from winding to winding without going through them all, or else because the winding has been cut in a place that is not near the end of the coil. The best way to determine if a motor needs rewinding is to fix every other possible thing wrong with it. Still, if the motor does not perform satisfactorily, then you might look at rewinding it. There are 2 main classifications of motors, AC and DC. AC motors require an alternating current or voltage source to make them work, like the power coming out of the wall outlets in our houses. DC motors require a direct current or voltage source to make them work, like the voltage coming out of batteries. Universal motors can work on either type of power. Not only is the construction of the motors different, but the means used to control the speed and torque created by each of these motors also varies, although the principles of power conversion are common to both. Now, though motors are broadly classified as AC and DC motors, there are many other classifications in motors, and we are going to see the rewinding procedure for some of these motors in the exercises that are to follow shortly. A table-type fan is a propeller-bladed fan having two or more blades directly driven by an electric motor. Generally, the rated voltage is 240 volts AC at 50 Hz frequency. Table fans are fitted with a single-phase motor, and it's either a shaded pole motor or a capacitor-type motor. In this exercise, we are going to learn to dismantle a table fan with a shaded pole motor, then dislodge the field winding from the poles and record the winding data.
The tools required for the purpose are electrician toolkit, nylon hammer, cold chisel, multimeter, 500 volt mega, weighing machine with a 3 kg range and 10 gram resolution, a pair of scissors, soldering iron, and hacksaw frame with a 30 centimeter blade. A shaded pole motor is a single-phase motor which has a squirrel cage rotor and a salient pole stator in which the field coil is wound. But first, we need to record the available details on the nameplate. Manufacturer's name, serial number, trade name, type AC or DC, voltage, frequency, input watt, oscillating mechanism, size of fan, that is sweep, RPM, number of blades, class of insulation, type of bearing, and bearing number. After making note of the details that you could gather from the nameplate, remove the guard from the fan body by loosening the guard clamps. Loosen the lock screw of the fan blade and remove the blade assembly from the shaft. Remove the oscillation mechanism lever screws. Unscrew and remove the rear guard and end nuts. Remove the end cover. Then, remove the rotor from the stator. Slip the rotor straight out without damaging the stator coils. Check the bearing for its proper functioning. Replace it if there is any end play. Clean the winding of the fan. Gather all the winding data that's possible and make note of it in the data sheet. Number of slots, number of poles, wire insulation, winding, hand or form, pole or slot insulation material, the size, type of lead wire size, type of sleeve and size. Make note of all the details that you could gather with regards to the winding.
In the case of a capacitor type table fan, the motor is a split phase type motor having starting and running windings. Split phase means there are two phases. No centrifugal switch is provided for the starting winding. The condenser is permanently connected in the circuit of the fan. In this exercise, we saw how to dismantle a table fan and dislodge the field winding from the poles, apart from gathering the various data from the table fan nameplate and its motor. exercise 1, we dismantled a table fan and removed the rotor from the stator. The stator is now ready for removal of the old winding and collection of necessary data for the purpose of rewinding. And that's what we are going to go through in this exercise.
The tools required for the purpose are cold chisel, ball peen hammer, combination plier, pincer, old power hacksaw blade, and wedge remover. The wedges can be removed using the wedge remover and the hammer. Place the stator in such a way that the non-connection end of the winding is facing you. Next, we need to cut the windings. Use a cold chisel for that. While cutting, care should be taken to see that the lamination is not damaged. Use the chisel end parallel to the core. Use pincers or pliers to pull out the wires from the connection end. Now, before cutting the coils, see that at least one coil in the form winding is not cut. This will be useful for the sake of measurement.
In this exercise, we have seen the procedure of stripping the old windings from the stator. Take care to use the tools specified for the purpose and follow the procedure demonstrated. In the previous couple of exercises, we learned how to dismantle a fan, remove the rotor and stator from it, and then remove the windings in them. In this exercise, we are going to see the procedure to prepare formers for making coils and the way to rewind the coils using those formers.
Talking about motor rewinding, some types of AC winding are diamond coil winding, skein winding, and concentric winding. In the case of diamond coil winding, the shape of the coil used is just like a diamond, and in this, the coil occupies more space. In skein winding, a long coil of sufficient length is first wound and then inserted in one slot. The remaining length is turned and inserted in the adjacent slots. In concentric winding, there are two or more coils in a group, and the coils in each group have the same center. In each group, the coil pitch is not equal and therefore do not overlap each other. Though it requires effort to insert the coils due to different coil spans, the design allows more cooling space. This type of winding is usually done in single-phase motor winding. Now, first, let's see how to make a former for diamond-shaped coils. Reshape the coil and measure the internal length and width directly, and then also measure the thickness of the coil. For making the winding frame, take a piece of wood of the same thickness as that of the coil and cut it to the length and width of the coil that we measured. File the edges until the coil snugly fits on the winding frame. The winding frame should be slightly tapered on one side to make it easy for the coil to slide out after it is wound. Now, for the side boards of the winding frame, take two pieces of wood larger than the winding frame. The length and breadth of these boards should be greater than the winding frame so as to accommodate the turns of the coil. Fix the winding frame centrally on one side of the side board with the help of screws. Let the tapered portion be away from the first side board. Next, fix the other side board on the winding frame centrally with the help of fixing screws. Make slots on the side board with the help of hacksaw so as to reach the surface of the winding frame. Now, mark the center of the assembly and drill a hole of M10 size. This is for mounting the assembly for winding purpose. Do not forget to insert twine threads through the slits before starting to wind. After winding the required number of turns, tie the twine threads over the coil to hold them tight. Remove the coil from the former by detaching the second side board. Do not make other coils unless the coil made is checked for its size and correctness. Insert the coil inside the slots of the stator according to the original pitch. The coil should neither be too tight nor loose in the slots. If it's not right, do the necessary modification in the former to correct it. Start preparing the required number of coils only after this. This completes the process involved in making a former and winding a diamond-shaped coil. Next, let's see how to make a former for skein winding. Take a wooden board of sufficient length and breadth to accommodate the prepared loop. Use 4 wooden spools and nail them onto the board. Hand wind the required number of turns of the skein. Make sure that you tie the turns together using a twine thread before removing the coil from the board. Do not make any further coils unless the size of this coil is checked for correctness. Next, let's see how to make a former for concentric coils. This type of winding has 2 or more coils in a group, and the coils in each group have the same center. This type of winding is usually provided in single-phase motors. Make formers like these and mount them on an adjustable sliding bracket. Each block should be assembled in such a way that they can be separated after the winding is completed for easy removal of the wound coils. Next, adjust the distance between the wooden formers according to the size of the measured wires and fix them in that position with a bolt nut system. Wind the required number of turns according to each coil in the set, starting from the smallest coil. It's important to tie the coils with twine threads at several places to keep the turns in position. Dismantle the blocks and remove the coils together. Place the coils in their respective slots, starting from the smallest coil. Use temporary wedges in the slots soon after the coil is inserted in the respective slot. After all the coils of the group are placed, check the distance between the coils as well as the overhang measurement. Proceed to make the other sets of coils only if this is found correct.
In this exercise, we learned to make formers for winding different types of coils and also learned to wind coils using them. First, we made a former for diamond-shaped coils and wound a coil using it. Next, we made a former for skein winding and also wound a coil. Then finally, we made a former for concentric coils and wound coils using it. In this exercise, we are going to see the procedure of inserting the coils in the slots. Now that we have wound coils using the formers fabricated for the purpose, next, let's see how to insert them in their respective slots.
Before that, we need to get the stator cleaned and insert slot liners in it. First, identify that stator side where the winding connections end is to be located. Then, position the stator in such a way that the connection ends of the stator are towards you. Next, identify the starting slot for beginning the winding. Insert the guide insulation paper in the identified slot. Hold the coil by the overhang ends and slide the turns in small bunches into the slots. The winding wire needs to fall inside the slot liner. See to it that no winding wire falls between the core and the slot liner. Also keep checking that the guide paper is in its position. Adjust the overhangs such that they are equal in both the sides. Finally, insert sleeves in the winding ends, remove the insulation, and connect the coils in series, solder the end connections, and pull the sleeves into position. Then, connect the lead wires, solder them, and insert sleeves on top of them. Bind the overhang and end connections with the help of a binding thread or a tape. Take care to check the dimensions of the overhang such that it's the same as in the original winding so that the winding does not rub with the rotor. Test the winding for insulation leakage, short, or open circuit.
In this exercise, we learned the procedure to be followed in inserting the coils in the slots. So far, we have learned to make formers for the sake of rewinding, then rewind coils using them, and then to insert these coils in their respective slots. The ceiling fan is one of the most commonly used home appliances, of which the motor is an integral part. A ceiling type fan is a propeller bladed fan having two or more blades driven by an electric motor and provided with a device for suspension from the ceiling of a room so that the blades rotate in a horizontal plane. In this exercise, we are going to learn to rewind the coil of a ceiling fan motor.
We shall be going through the process of dismantling a ceiling fan, stripping the coils from the fan, preparing the winding table and developing a diagram, preparing the slot liners and inserting them in the slots, laying the coils in the slots and insulating them, making end connections as per data extracted, soldering and insulating the end connections and leads, binding with a tape and shaping the overhangs, preheating and varnishing the winding, and finally assembling and testing the ceiling fan. The tools required for the purpose are nylon hammer, screwdriver, insulated cutting plier, DB knife, multimeter, 500-volt megger, hacksaw frame with a 30 centimeter blade, soldering iron, and scissors. First, note the nameplate details of the ceiling fan and make an entry of the same. Manufacturer's name, serial number, voltage, frequency, type AC or DC, watts, size of the fan, RPM, number of blades, type of bearing, bearing make, and class of insulation. Then, unscrew the fasteners and remove the fan blade. Take care to store the blades safely such that they don't get bent. If the blades get bent, they will produce unusual sound and airflow too will get reduced. Observe the connections in the terminal box. Mark them in a separate sheet of paper and disconnect them. Dismantle the fan and remove the stator. Take care to retain the removed screws and the loose parts in a separate tray. Untie the end connections from the winding. Trace the connections and draw a diagram of the same for your record. In the diagram, you need to indicate which wiring is in the inner slot and which one is in the outer slot. Enter all these details in the data sheet. Length of coil in millimeters, width of coil in millimeters, starting winding is kept in so many slots, overhang measured from the end of the core, type of binding, capacitor, all these things. Measure the overhang dimensions from the edge of the core and enter the details in the table. Also record the type of binding in your data sheet. Thick leatheroid paper is used instead of wedges in some fans. Finally, cut the overhang end of the coils in the middle at both sides of the core. Remember to leave one coil each in the starting and running windings for the sake of measurement. Remove the coils by pulling the cut ends with the help of pincers or pliers. Take care to record the type, size of wire, and number of turns used in both the windings. Measure the weight of both the starting and main windings separately, and then measure the total weight of the coils and make a note of them. Set the core if it's mangled and clean the slots. Check the bearing, and if it's found faulty, replace it. Get insulation paper of the same grade and size and prepare the slot liners in the required numbers. Then insulate the slots with the prepared slot liners. In the case of a ceiling fan, generally the size of the running and starting winding will be the same. Wind the coils, taking care to maintain the same turns and the same size of the wire. After confirming their sizes, make the required number of main and starting winding coils. Please follow the coil throw as notified in the data sheet for the fan that you are servicing. Remember to start winding in the inner slots. Keep proceeding in the same manner till you have inserted all the coils in the inner slots and wedged them. Now, the starting winding. Proceed in the same manner till you have inserted all the starting winding coils in the outer slots and wedged them properly. Finally, insert sleeves in the winding ends remove the insulation and connect the coils in series according to the connection diagram which you have made earlier. Check that the connections are as per the diagram. Solder the end connections and pull the sleeves into position. Then connect the lead wires, solder them and insert sleeves on top of them. Bind the overhang and end connections with the help of a binding thread or a tape. Take care to check the dimensions of the overhang such that it's the same as in the original winding so that the winding does not rub with the rotor. Using a megger and a multimeter, test the winding for insulation leakage, short or open circuit. Assemble the fan and run it for a few minutes. If the rotation is found satisfactory, dismantle the fan, preheat and impregnate the winding with varnish. Allow it to dry and then remove the excess varnish. Reassemble the fan and test the fan for its performance for at least 8 hours. Check for the direction of rotation. When viewed from the bottom, it should be anti-clockwise. If found incorrect, you can correct it by changing the connections of either the starting or running winding.
That brings us to the end of this exercise on winding a ceiling fan motor. I hope that having gone through this exercise, you will now be aware of the procedure to dismantle the fan, strip the coils, extract data, wind the coils using a proper former, lay the coils in their respective slots, reconnect, insulate, and test them for their proper working.
नमस्कार, आपका स्वागत है इसी लैंग्वेज के तीसरे अध्याय में। मैं हूं आपका प्रशिक्षक कौशल किशोर शर्मा, प्रधान तकनीकी अधिकारी सीडेक पुणे। आज हम बात करेंगे डिसीजन मेकिंग सिंटैक्स, इफ, एल्स, स्विच,